All right, guys, in problem number 4, and again, this is in 2019, we are dealing with a cylindrical barrel, gotcha, with a diameter of 2 feet. The interesting thing right off the bat is the fact that this tank, this barrel, is a cylinder, which means that the radius here is always going to remain constant. If our diameter is 2 feet, then our radius is 1. And in most of the problems that we did like this, back with related rates in section 3.10, usually it was a tank that was something like a cone where both the radius and height would be different going on. So that might be important right here. But anyway, water is draining out through the bottom of the tank, gotcha, and they've given you the rate of change of the height of the water in the barrel is given to you by this derivative right here, negative 1/10 times the square root of h. Then they were kind enough here to tell you the formula for volume of a cylinder, which of course everybody knows from geometry anyway, is pi r squared h. Okay, 3 parts to this problem, guys. Find the rate of change of the volume of the water in the barrel when the height of the water is 4 feet. This sounds like a pretty straightforward related rate problem to me. So we know we were given in a problem like this right here, the derivative, wait, I forgot already, the derivative of height with respect to t. So dh dt is equal to a negative 1/10 times the square root of h. Interesting, because usually that's done in terms of this lower variable right here, so I'd expect that in terms of t, but okay, gotcha. Negative 1/10 times the square root of h. And the derivative we want to know right here, find the rate of change of the volume of the water in the barrel at the time when the height is 4 feet. So we want the derivative of volume with respect to t at the moment when h is equal to 4 feet. Okay, that might be a little bit more interesting than I thought at first. Indicate units of measure. All right, so what we need, everybody, is an equation that relates height with volume. And that's the volume equation they gave us here, that volume is equal to pi r squared multiplied by h. Now, what was often the case right here when we did these problems back in 310 is that you knew either dr dt or dh dt, but not both. But what we can take advantage of right here is the fact that in this tank, we said the radius of water is always equal to 1. That is a constant value, which means that it is not a time-specific value, which we talked about back in the day. That means that we can use this r value right here, because no matter where we are with water in the tank, the radius is always going to be 1. So pi times 1 squared times h means that volume, that's interesting, is just going to be pi times h. All right, guys, in that case then, let's differentiate with respect to time. The derivative of volume with respect to time is going to equal pi times dh dt. Okay, so we wanted dv dt at the time when h is equal to 4 feet, but I don't think that 4 feet is actually important here at all because there is no h within this figure right here. So our derivative of volume with respect to time then is going to be pi times dh dt, which is negative 1/10 times, oh, here you go, times the square root of h, but that's it. I'm sorry, guys. It's when h is equal to 4 feet. So we put the 4 in there. Okay, so what does that do for us? The square root of 4 is 2. 2 times a negative 1/10 is a negative 1/5. Times pi, it's going to be a negative pi over 5. And they did say to include units of measure right here. So if volume in this problem, let me go back and check here, volume was being measured in, wait, I think it says that here, h is measured in feet, t is measured in seconds. So volume would be cubic feet. All right, that's what's going on here for dv dt. So cubic feet, and time was being measured in seconds. So that would be our answer for part A there. Negative pi over 5 cubic feet per second. Interesting. You don't see many there, guys, where that value of h shows up within that derivative that was given to you. Usually that derivative is a constant then. Okay, interesting. All right, back to part B now. When the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing. And we've got to explain our reasoning right here. Okay, so this is what we have here then, guys. So let's take a look. When they ask you if a rate of change is increasing or decreasing right here, it would be a question of the derivative being positive or negative. So that's what we've got to work on. So when the height of the water is 3 feet, they want to know if dH dt right there, the rate of change, if that is positive or negative. Okay, so what I think we're going to have to do on part B here is actually take the derivative. This tells you the rate of change of the height here, but we want to know if the rate of change of that height is increasing or decreasing. So we need our second derivative in this problem here, guys. So for part B, let's write this down again. The derivative of height with respect to time was equal to, and that was a negative 1/10 times the square root of h. We're then going to differentiate this again. d2h over dt2 would equal, now here we go, guys. Now remember, we're differentiating with respect to t. So this could be rewritten as a negative 1/10, and then that would be an h to the 1/2. So the derivative of that would be a negative nope, that's not what I meant to write. A negative 1/20th, that's 1/10 times 1/2, times h. We drop the power by 1, that's now a negative 1/2, and then times the derivative within. And that would be the derivative of h taken with respect to time. So we can clean this up a little bit to make this a negative 1 over 20 times the square root of h. But that then gets multiplied by dH dt, which was this quantity right here, a negative 1/10 times the square root of h. Okay, so now the negatives cancel each other out and we just get a positive, but more importantly, the root h's cancel each other out, and I end up with a positive 1 over 200. So that would be the value now of the second derivative here of height taken with respect to time. Now, what we wanted to know is whether the rate of change of the height is increasing or decreasing. So we checked its derivative, and this derivative, ever so slightly, is positive. So we can say right here, guys, that since d2h over dt2 is greater than 0, really, it's greater than 0 all the time, but I would normally say at the moment in question right here, at the time when h is equal to 3 feet, then we can conclude that, and let me get the wording right here, guys, the rate of change of the height of the water, oh boy, the rate of change of the height of the water, okay, gotcha, with respect to time is increasing. Okay, with respect to time, gotcha, is increasing at this, I'll just say at this moment, and we'll call that good enough. So the important thing is there, guys, we got that it was increasing, and we explained and showed it's because the derivative of that function right there the derivative of our derivative ended up being positive. Okay, and on to the third part right here. At a time of t equals 0 seconds, the height of the water is 5 feet. Sounds like an initial condition right there. Use separation of variables to find an expression for h in terms of t. Oh, okay, so they want us here to take that derivative then. So once more, the derivative of h with respect to t was equal to a negative 1/10 times the square root of h, and they want us now, guys, to solve this differential equation, right? So let me make sure I've got all that right. Negative 1/10 square root of h. Okay, so let's do it, guys. We need to separate our variables, and we want, let's see, all the h's and the dh on the left, all the t's and the dt on the right. So we're going to divide both sides by the square root of h, and then we'll multiply both sides by dt. That cancels with that, this cancels with that, and that's going to leave us now 1 over the square root of h, which is h to the negative 1/2 power dh, and that equals, all right, we've got a negative 1/10 dt. So there's our separation of variables. Now we'll go ahead and do an antiderivative on both sides here. So on the left, we have h. We raise the power by 1/2, and we divide by that new power. That puts a 2 out in front for us. Equals. Now, integrating a constant, this is just going to be a -1/10 t, and here's where we put our plus c. Now is when I like to switch to green and use my initial condition. At a time t equals 0, the height was equal to 5. So when t is 0, that tells us then that h has to equal 5. So 2 times, that'll be 5 to the 1/2, or the square root of 5, is equal to a -1/10 times 0 plus c. Well, there you go. C is equal to 2 root 5. So back to where we were just a second ago, 2, I'll go write that as the square root of h, doesn't really matter, is equal to a -1/10 t plus a 2 root 5. And now we need to keep plugging away here, guys, and we need to solve this thing. I believe it was solving for h in terms of t, correct? Yeah, that's what we were looking for. So we're going to divide, let's go red here, everything by 2, this term, and this term, and this term. So we'll now end up with the square root of h is equal to, that's now a -1/20th t, and then those 2's cancel here and here, and we just get a plus root 5. And now, this is a little ugly, we're going to square both sides. Remember, guys, though, that squaring happens on the entire side at a time, not just term by term. So that left side is just going to be h, but on that right side, yeah, we're going to leave it the way it's written there, guys. -1/20th t plus the square root of 5 quantity squared. And my 5 looks like a 6 right there. Sorry about that. Square root of 5, and that's as good as it gets for coming up with a formula here for h in terms of t. And I think that's everything they asked us to do right there. All right, guys, so that's a wrap on question number 4.